Hello friends, in the last video we had discussed in general about air refrigeration system and in brief about Bell-Coleman cycle. So today I am available with a new video related to vapor compression refrigeration system. If you want to see the previous video, the link is available in the description. Please go through that. Vapor compression refrigeration system is also known as mechanical refrigeration and it is widely used for domestic as well as for commercial utility viewpoint. It is also known as vapor compression refrigeration, that is VCR cycle. In the air refrigeration system, the COP of the system is very low and therefore to achieve COP of refrigeration system close to the ideal value, the phase change cycle and the vapor compression refrigeration cycle is the suitable choice. In above case, the working medium or the refrigerant is changing the phase during the cyclic process. So now we have to discuss about VCR cycle in which the phase change is observed during the cyclic process. Based on following thermodynamic principle, the VCR cycle is designed. First, heat will always flow from higher temperature to lower temperature, that is called spontaneous process. Second, the fluid absorbs the heat to change the phase from liquid to vapor and it rejects the heat to again convert back into the liquid from vapor. Third, for the fixed value of pressure, the vaporization of one particular fluid takes place at constant temperature. The vaporization temperature at constant pressure is different for different fluids. And fourth, heat energy and other form of energies are mutually convertible with the directional relationship imposed by second law of thermodynamics. So now we will discuss in detail about simple vapor compression refrigeration system, components, design, working, representation on TS and PS diagram as well as its analysis. Figure number 1 depicts the schematic diagram of simple VCR cycle where you find 4 major components that include first hermetically sealed reciprocating compressor, second condenser, third expansion device and fourth evaporator. So we will start with the process 1 to 2. So it's state 1, low pressure, low temperature refrigerant in vapor form is available that will enter into the compressor. Why I am telling that it is a low pressure, low temperature refrigerant in vapor state? Because the compressor can handle only compressible fluid. If there is a wet vapor or if there is a liquid, in that case the compressor cannot handle the wet vapor or liquid, and hence at state 1 low pressure, low temperature refrigerant in vapor state is available that will enter into the compressor. So at state 2 we will get high pressure, high temperature refrigerant in vapor form. So again I am repeating, at outlet of the compressor is high pressure, high temperature refrigerant in vapor state. Now the second component is a condenser. In our domestic refrigerator, condenser is located at back side of the refrigerator. Generally it is a non-contact type of heat exchanger in which the hot fluid is high pressure, high temperature vapor refrigerant and the cold fluid is surrounding air. So now the heat exchange takes place between the refrigerant and the air, and because of that at state 3 low temperature, high pressure refrigerant in liquid state is available. So again I am repeating, at state 3 high pressure, low temperature refrigerant in liquid state is available. Now expansion device is available between state 3 to 4. So expansion device is the device in which the expansion of the refrigerant is observed. It is isenthalpic process, and in detail we will discuss when we will go for expansion process in detail. So what we'll observe here at state 4 is the refrigerant which is available at state 4 is low pressure, low temperature refrigerant in wet condition. So now at state 4, low pressure, low temperature wet vapor of the refrigerant is available, or sometimes the liquid is available. Now the fourth component is evaporator. Generally in our domestic refrigerator, the evaporator is located in the ice box, and you had observed that the ice box is not designed with a flat shape, it is always embossed. And it is embossed because in that portion the refrigerant is flowing. And we know that in the ice box we'll put ice cream, or you can say tray of water, or you can say other commodities which we want to maintain at lower temperature. So now the system requirement at state 1 is low pressure, low temperature vapor, and what is available at state 4 is low pressure, low temperature wet vapor or a liquid. So now if either it is a wet vapor or it is a liquid, it has to convert into vapor, and to do that it has to absorb the heat. So what this refrigerant will do is, the refrigerant will absorb the heat from the commodities which are placed in the ice box. Suppose the tray is available with the water. In that case, the refrigerant will absorb the heat from the water. The water is converted into ice because the water will reject the heat, so it converts into solid. At the same time, the refrigerant will absorb the heat from the water and it convert into vapor, and this cycle will continue. So you can see in the schematic diagram, the line AA and vertical line BB is shown. The line AA, that is above the line AA, you will observe high pressure. So in the previous diagram, above the line AA, high pressure zone is there. Below the line AA, you will observe low pressure zone is there. On the left side of line BB, you will observe refrigerant is available in liquid state, whereas on the right side of line BB, you will observe the refrigerant is available in vapor state. Now you can see the representation of vapor refrigeration cycle on the TS and pH diagram, that is temperature entropy diagram and pressure enthalpy diagram. So 1 to 2 is the compression process, where you will observe the refrigerant is available in superheated state, then it will lose the heat and it will reach to state 3. It is a dry saturated liquid. Then 3 to 4 is expansion process, and 4 to 1, that is evaporation process, that is our refrigeration effect. So 1 to 2 is a compression work required, 2 to 3 is a heat rejection process, 4 to 1 is heat absorption process, whereas 3 to 4 is isenthalpic process, where H3 is equals to H4. Now in detail we have to discuss about all the 4 processes and what are the major component of VCR cycle. You can see the 4 major component of simple VCR cycle includes compressor, condenser, expansion device and evaporator. In simple VCR cycle, 4 fundamental processes are there to complete one cycle, that include compressor, condensation, expansion and evaporation. So as we had discussed, 1 to 2 is a compression process. We have to supply work to the compressor. The compressor will compress the vapor refrigerant, and at outlet we will get high pressure, high temperature refrigerant in vapor form. Now according to the steady flow energy equation, if you want to know what is the compression work, then WC, that is equals to H2 minus H1. The unit is kilojoule per kilogram, where H2 is enthalpy of refrigerant at the temperature T2, that is after compression. And if the enthalpy of the refrigerant vapor is the superheated one, then H2 is obtained with the equation H2, that is equals to Hg plus Cp of steam into superheat temperature minus saturation temperature at P2 pressure. If the enthalpy at state 2 is a dry saturated vapor, then H2, that is equals to Hg at P2 pressure, and H1, that is enthalpy of refrigerant vapor which is entering into the compressor at inlet with the temperature T1, then at 1, that is equals to Hg at P1 pressure if the vapor is dry saturated one, or H1, that is equals to Hf plus X HFG at P1 pressure if the wet vapor is entered into the system. But generally entry of wet vapor in the compressor is not desirable at all. Now the second process which we will observe is the condensation process that will occur in the condenser of the refrigerator, and we know that condenser of the refrigerator is a non-contact type of heat exchanger. The high pressure, high temperature refrigerant vapor will enter into the condenser and it will exchange the heat with the surrounding air. Because of that, what happens is we will get high pressure, low temperature, liquid refrigerant at outlet of the condenser. As the condenser is a heat exchanger, we have to find out what is the steady flow energy equation for condenser. Heat rejected by the condenser, that is equals to heat gained by the air, and heat rejected is considered as -1. So Q2, that is equals to H3 minus H2, where H3, that is enthalpy of the saturated liquid available at outlet of the condenser at P3 pressure, and the H3 value, that is equals to HF, that is at P3 pressure for saturated liquid refrigerant. Now the process 3 to 4 is the expansion process that happens in expansion device. So what you will observe is during expansion process, the pressure drops from P4 to P4 equals to P1. So the pressure initially was P3 and that is dropping to P4, and in this case you will observe that it is isenthalpic process. So enthalpy of the fluid before throttling and after throttling remains same, and in the modern domestic refrigerator a capillary tube, that is a small bore tube, is used in place of expansion valve. So you will observe between the process 3 to 4, that is before expansion device and after expansion device, the pressure of the refrigerant will drop, and because of that at outlet we will get low pressure, low temperature, liquid or wet refrigerant. If you want to know what is the steady flow energy equation for expansion device, it is H3 is equals to H4, where H4, that is enthalpy of wet vapor at exit of expansion device, and to find out H4 we have to use the formula H4 is equals to HF4 plus X4 HFG4 at P4 pressure. The unit is kilojoule per kilogram. The last process 4 to 1 is evaporation process that occurs in evaporator. Again, it is a non-contact type of heat exchanger that is available at our ice box. During the evaporation process, the liquid vapor refrigerant absorb the latent heat of vaporization from the medium that is available in the ice box, either it is a brine, water or ice cream or any other commodity, and the heat which is absorbed by the refrigerant is called refrigeration effect, or it is called RE. So in the evaporator we will observe RE, that is refrigerating effect. If you want to derive steady flow energy equation, in this case for the evaporator it is QA, that is equals to, you can say, H1 minus H4, and now we have to find out what is the coefficient of performance, that is COP, that is ratio of effect divided by effort. So our effect is refrigerant effect and effort is compression work. So it is RE divided by WC, and that is, you can observe H1 minus H4 divided by H2 minus H1. So friend, this was about theory related to simple VCR cycle. Now we will discuss what are the advantage and disadvantage of VCR cycle over air refrigeration system. So in that, first we will discuss about advantage. So first advantage, COP of VCR cycle is higher. Running cost is very low compared to air refrigeration cycle. The size of the evaporator required in VCR cycle is very small. compared to the air refrigeration system for same value of RE, and last is easily controllable expansion due to the control of expansion valve. If we talk disadvantages, first is higher capital cost is required, inflammability, toxicity and leakage of refrigerant, as well as effect of suction pressure. These are major disadvantage of simple VCR cycle. Now we will discuss what are the factors affecting the performance of VCR system. So first is, you can say, effect of superheating, effect of subcooling or undercooling, effect of suction pressure, effect of discharge pressure or delivery pressure, air leakage, as well as effect of suction temperature and condenser temperature. So now in the next slide, in detail, we have to discuss about what is the effect of these parameters on COP of VCR cycle. Now we will discuss about the effect of various parameters on COP of VCR cycle. In lot many competitive examination include UPSC, GPSC and all PSU exam, MCQ may be asked. So you should pay your attention here. So first part is, what is the effect of superheat vapor on COP of the system. So you can see our initial cycle was 1, 2, 3, 4, and now our cycle is 1 dash, 2 dash, 2, 3, 4, 1, 1 dash. So when we'll go for superheating, the 1 dash, 2 dash is telling superheated state of the steam. So what is its effect? That is shown in the next slide. So you can see, when we'll go for superheating, the effect of superheating is increasing the refrigerant effect at the cost of compression work. So if we talk about COP, that is RE divided by WC, and what you will observe is the value of RE, that is the refrigerant effect, will definitely increase, but against to that, the compression work which we have to supply is very high, and because of that, the overall effect of superheating is lower value of COP. So if we go for superheating of this refrigerant vapor, in that case COP of VCR cycle is decreasing. Now we have to discuss what is the effect of subcooling or undercooling on VCR cycle. Our initial cycle was 1, 2, 3, 4, 1. Now our new cycle with subcooling or undercooling is 1, 2, 3, 3 days, 4 days, 4, 1. So now what is the effect of subcooling? You can see the 3 to 3 days and 3 days to 4 days, 4 days to 4, that is a subcooling. So now what is the effect of subcooling on COP of the system? That we have to find out. So can you guess what is its effect on COP? Yes friend, you can see subcooling is the process of cooling of liquid refrigerant below the condensing temperature for a given pressure. So we are not changing the pressure and we try to reduce the temperature of liquid. So how that is possible? So the subcooling or undercooling may be either possible by circulating the greater quantity of cooling water through the condenser, or using the water which is colder than main circulating water. The subcooling or undercooling result in increase in refrigerant effect without changing in compression work. So definitely when you go for undercooling, the COP of refrigeration system will increase because RE will increase without affecting the compression work. Now what is the effect of suction pressure, that we have to find out. So our initial cycle was 1, 2, 3, 4, 1. Now our cycle, you can see it is 1 days, 1, 2 days, 2, 3, 4, 4 days, 1 days. So now you can see from the diagram and you have to tell what is effect of reduction in suction pressure. Can you think? Yes, you are absolutely correct. The reduction in suction pressure caused reduction in refrigerant effect at the cost of rise in the compression work. So in that case, what happens to the COP? RE will decrease and WC will increase. So there is a huge drop in coefficient of performance, that is on COP. Now, what is the effect of discharge pressure or delivery pressure that we have to find out? So you can see initial cycle was 1, 2, 3, 4, 1. Now our new cycle, that is with rise in the delivery pressure, is 1, 2 dash, 3 dash, 4 dash, 1. So now I hope you can guess what is the effect on COP. Can you tell me what is the answer? Yes. When we'll go for increasing in the delivery pressure, definitely the refrigerant effect will decrease and the compression work will increase. So the COP will decrease. So it is not desirable to increase the delivery pressure. Now, what is the effect of leakage of air into VCR cycle? That is shown here, A and B. So air has a very poor heat transfer coefficient that causes the reduction in heat transfer at the condenser and evaporator, and the presence of air destroy the vacuum required in the evaporator, and hence COP of VCR cycle will reduce. So it is always desirable that the leak proof system we have to design so air cannot enter into the system and COP will not be affected. The effect of suction temperature and condenser temperature. The refrigeration system should always be designed to operate at the highest possible suction temperature and the lowest possible condensing temperature, with keeping given the requirement of the application in the mind. Now friend, we have to solve some basic sample numericals related to simple VCR cycle. Now you can see the first numerical. So in the simple saturated VCR system, evaporator temperature is minus 15 degrees Celsius and condenser temperature is plus 30 degrees Celsius. R12 is used as a refrigerant. Determine first COP of the system, mass of the refrigerant per second per ton. Represent the said system on TS and PS diagram. For R12, the properties from the property table are given, that is at minus 15 degrees Celsius, the pressure, Hg, Vg, Sg values, as well as at plus 30 degrees Celsius, the pressure, then Hg, Sg, Vg, Hf values are given, and assume the Cp, that is specific heat of R12, is 0.629 kilojoule per kilogram Kelvin for the superheat region. So these many things are given in the data. We have to find out what is the COP, mass of the refrigeration per second per ton. Two things we have to find out. So now first we will plot the entire system on TS and PS diagram, and then we will try to solve the problem. So you can see, firstly we had plot the same thing on the TS and PS diagram. In the data itself it is given the refrigerant is in superheated state. So 1 to 2 process is shown, where at state 2 the refrigerant is available in superheating zone. The same thing is plotted on the pH diagram also. Now for theoretical saturated VCR cycle, S1 that is equals to S2 and that is equals to Hg plus Cp into Ln, superheat temperature divided by saturation temperature at condenser pressure. So we will get the superheat temperature, that is 38.16 degrees Celsius, but very important thing here is we have to convert both the temperatures in terms of Kelvin, and then we have to put the data. So in the data the value of S1 that is equals to S2 that is available, that is 1.56323, that is given in the data for the condenser pressure. So superheat temperature at state 2 is available, that value is 38.16 degrees Celsius. Now H1 that is enthalpy at inlet of the compressor, that is equals to Hg, that is at evaporation pressure, and that is available 344.927 kilojoule per kilogram, that is given in the data. Now we have to find out what is the value of H2, that is enthalpy at state 2, that is for superheated refrigerant, that is equals to Hg plus Cp of refrigerant into superheat temperature minus saturation temperature at condenser pressure, and that value is obtained, that is 369.66 kilojoule per kilogram. So our compression work is H2 minus H1, and that value is 24.733 kilojoule per kilogram. So now H1 and H2 is available. Based on that, we will get what is the value of WC. Now our next target is to find out H4. So when H4 is available, definitely our refrigerant effect is available. So we know that H3 is equals to H4. So and H3 value, that is equals to HF at condenser pressure, and that value is enthalpy of saturated liquid, that is 228.538 kilojoule per kilogram. So our refrigerant effect is H1 minus H4, that is 116.389 kilojoule per kilogram. So now first, what is the mass of refrigerant circulated, that is 3.156 into ton of refrigerant divided by RE. So that value is 0.0302 kilogram per second per ton, and COP, that is RE divided by WC. So we will get the COP value, that is equals to 4.705. Now you can use the pH chart, and with help of pH chart directly you will get all four enthalpy values, and when all four enthalpy values are available, directly you can calculate what is the COP. So your task is to find out COP with another method, that is alternative method. Use the pH chart and find out what is the answer. I hope you will get the same answer. Please try at your home to solve this problem with pH chart. Now we'll talk about second numerical. A theoretical Vcr cycle works between minus 7 degrees Celsius and 27 degrees Celsius. The vapor is dry and saturated at the end of reversible adiabatic compression. Assuming no undercooling and evaporation by the throttle valve, determine COP, power required by the compressor to remove 3 kilojoule per second of heat. The properties of the refrigerant are given in the table. So enthalpy values and entropy values are given in the table, and we have to find out some answers. Here the entropy unit is kilojoule per kilogram Kelvin. So first we have to find out what is the value of H2 at condenser pressure. So H2 value, that is equals to HF plus X HFG, and that value will get, that is 1288 kilojoule per kilogram. H3, that is enthalpy of saturated liquid at condenser pressure, that is equals to 115 kilojoule per kilogram, that is equals to H4. So the COP value which we will get, that is RE divided by WC. So first of all, we have to find out all the four enthalpy values. So to find out the value of H1, first we have to find out what is the dryness fraction at state 1. So we have to use the formula S2, that is entropy at state 2, that is equals to entropy at state 1, that is equals to SF1 plus X1 SFG1 at evaporator pressure. So all the values are available here. So based on that, we will get what is the dryness fraction at inlet of the compressor is 0.91. So we will get H1, that is equals to HF1 plus X1 HFG1, and that value is 1151.18 kilojoule per kilogram. Based on that, we will get the COP value, that is 7.57. Now The heat required to remove 3 kilojoule per second, that is refrigerant effect, is given. So RE, that value is 3, and that is equals to m dot into H1 minus H4. So H1 value is available, H4 value is available, RE is available. So we'll get the mass of refrigerant circulated in the system, that is 0.174 kilogram per minute. And the work done by the compressor, that is WC, that is m dot into H2 minus H1, and that value is 0.397 kilowatt. Friends, in this way we have to solve other problems related to simple VCR cycle. The problems are much easier, but somewhat practice is required from your side. This topic was taken from Refrigeration and Air Conditioning by Professor Alpesh V. Mehta and Professor Pinkal G. Choksi, Atul Prakashan. So friends, stay home, stay safe, and soon I am going to upload a new video related to engineering thermodynamics. Have a nice day. Thank you.